Today we'll explore explainable neural networks and the process they use to compute simple functions. A key factor in understanding a neural network's calculations lies in the weights it selects. Let's begin. Here we use a basic example. A neural network designed to calculate the logical AND function. It takes two binary inputs and produces one binary output, either a 0 or 1. While we obviously don't need a neural network for such a straightforward task, it's perfect for understanding how these systems operate. So, let's build a simple neural network designed to compute the logical AND function. With just two binary inputs, our network produces a single binary output, either a 0 or 1. The inputs we use are pairs, 0, 0, 0, 1, 1, 0, and 1, 1. The challenge is determining the right weights, theta 0, theta 1, and theta 2 to achieve the correct output for each input pair. So our challenge is to find weights that can be used to compute AND function. Now suppose we apply each of the input pairs of x1 and x2 to the h theta x equation. We get this fourth column as expressions in theta 0, theta 1, and theta 2. When compute h theta x for x1 and x2 with some weights, we get some integer values that may be large. We need to apply an activation function that can map large numbers to a value between 0 and 1. Although there are different activation functions, we will choose the sigmoid function which is shown. After applying the function to h theta x, if we get a value greater than 0.5, we will call it a 1, otherwise 0. Sigmoid function is perfect for determining binary output 0 or 1, as the curve is very close to 0 or 1 for most values. For the first input pair, 0, 0, we plug in 0 for both x1 and x2, and we get h theta x is equals to theta 0. Since we need the output to be 0, we need to choose a negative value for theta. Any negative value would do at this point, but later we need to pay attention to other conditions as well. Now, for the second input pair, 0, 1, we get h theta x is equals to theta 0 plus theta 2. Since we need the output to be 0, we need to choose a negative value for theta 0 plus theta 2. This can be one positive, one negative combination, or both negative, at least for now. Now take a look at all four inequalities. What values for theta 0, theta 1, and theta 2 can be chosen so that all four conditions are satisfied, and there are many such combinations. Here we show three possible combinations of values for theta, 0, theta 1, and theta 2 that can be chosen. As shown in the table, all of them satisfy the four conditions that is required for the neural network to compute the AND function. In this case, we can choose to go with -1, 0.5, and 0.5 for theta 0, theta 1, and theta 2. But any other combinations can work as well as long as it can satisfy the four conditions. Now let's use the same neural network to compute the OR function. As before, we need to find values of theta 0, theta 1, and theta 2 that can work. By following the same computations as before, we find the constraints for theta 0, theta 1, and theta 2 that needs to be satisfied in order to get the values for the OR function as shown by the table. In the first case, when x1 and x2 is 0, we need a 0. Otherwise, we need 1. Therefore, we need to find a set of values for theta 0, theta 1, and theta 2 that can satisfy the four inequalities, as shown by the column named conditions for output. If you'd like, pause the video and think of a solution. So here are three possible value pairs, all of whom can satisfy the four inequalities. Hence, any one of them should work fine. So let's go with -1, 2, 1 for theta 0, theta 1, and theta 2. So again, we use the same neural network, but by changing the weights, we can make it calculate a specific function. This is how large neural networks do their own computation. But instead of doing mathematical analysis like we did and finding the values of weights, large networks learn from data, and they can compute complex functions that we are not capable of programming. So now let's ask the question, how do we compute the not function or negation? Let's take a look. Unlike the AND and OR functions, the NOT function involves just a single input, which it inverts. So if the input is 0, the output will be 1, and vice versa. Think of this network as a switch that flips the signal. The challenge lies in setting the right weight and threshold to achieve this inversion accurately. Now, our function h theta x is simple and only depends on one binary input x. By looking at the two equations, we can easily find two weights, theta 0 is 1 and theta 1 is minus 1, that can satisfy the required conditions. Now here is an intriguing question. Can a neural network with a single hidden layer compute the NAND function? This might seem complex. And remember, the NAND function is a fundamental building block in computing. It outputs 0 only if both inputs are 1. Otherwise, it outputs 1. Our task is to determine how to configure this network so it mirrors the NAND logic. Think about this, and we will discuss NAND function in the next video. Hint, you might need more than one neuron to do this. Until next time, enjoy understanding how neural networks work.